Hello everyone. In this video, we're going to explain the transmit and receive channel models in wireless communications. In a basic wireless communication system, we have multiple users, and each one of those users wants to transmit their own data using the same channel, which is the air. So, for the data of those users to not interfere in the air, we usually assign each one of them different carrier frequency. So, let's say we assume carrier frequency F1 to user 1 and F2 to user 2, F3 to user 3, and F4 to user 4. So the transmitter and the receiver at any point they are gonna recognize any data transmitted around carrier frequency F1 to be the data for user 1. Any data around the carrier frequency F2 is going to be associated with user 2, and so on. And we call this process modulation. Okay, now let's see how the signal looks like if we apply this modulation thing. So we want to transmit a sequence of bits. Let's assume we have 8 bits here that we want to transmit using electromagnetic waves. So one of the most well-known modulation technique is called QAM, or quadrature amplitude modulation, and I'm going to explain this QAM in more detail in a future video. But let's assume this mapping is given from bits to complex numbers. Okay, so if you see that we have like each 4 bits are assigned one complex number in this complex plane, but they are in a format of 4 bits. So if we have 8 bits, as we have in this sequence over here, we simply divide them into 2 sequences, and each of these sequences has only 4 bits. Okay. Then we do the mapping. We try to look for this sequence, 1101. Where is it in this plane? It is over here. This sequence is associated with this complex number 1 minus j. So the real part is in the x-axis and the imaginary part is in the y-axis. And we usually in communication we call the real part the in-phase component, and the imaginary part the quadrature component. Okay, then we have the second sequence over here, which is 0110. Again, we try to find it in this map over here. It is here, and this is associated with -1 plus j3. Okay, so if we have multiple of those bit sequences, let's assume that we have 4 over here, and we already mapped them with their corresponding complex numbers, or in-phase and quadrature components, as we call them in wireless communication. Now we want to transmit this to the receiver, and it's impossible to transmit them in this form because they are complex number. They have imaginary part. They are not real completely. So the question is, how can we transmit those signals to the receiver? And we need to do the modulation as well. We need to transmit them in certain carrier frequency. So to do that, we will take the in-phase part and plot it for those numbers, and we are going to take the quadrature parts and plot them as pulses. So for example, let's take the real part here. We have 1, 3, -3, and -1. What we are going to do is we are going to call this the in-phase part of the signal, is IT, and we are going to plot it as pulses. For example, we're going to have the first pulse, the first pulse has a value of 1. So this is a pulse that has a value of 1 and duration of capital T, and this is a pulse duration. Then the second pulse is going to be 3. So this is a pulse that has a value of 3 and duration of T as well. So this is going to be 2T. Then the third pulse is going to be -3, and the fourth is going to be -1. So this is the third pulse over here, and it has a value of -3. And this is the fourth pulse with a value of -1. And we are going to do the same for the quadrature components. We're going to take the 4, plot them as pulses, and they are going to have the same duration, basically. Okay, and this one is 40. It is usually useful to look at things in the frequency domain as we do all of these time domain analysis, because we are going to use the frequency domain analysis a lot in the future. Okay, so if you want to plot those signals in the frequency domain, remember the pulse is just a rect signal. And if we want to take the magnitude of like the frequency response of a rect signal, is going to be a sync signal. Okay, so this is how this pulse is going to look like in the frequency domain. And this point over here has a relation with this point over here. It has a value of 1/t. So if you want to find the effective bandwidth of the signal, like where most of the energy is concentrated, it's going to be in this area, and it's going to be 2/t. We have 1/t here and another 1/t over here. So we have 2/t. We can do the same analysis for the quadrature part, and this is it's going to have a bandwidth of 2/t as well. Okay, so we call the signal ut, which is the in-phase component, plus j multiplied by the quadrature component. We call this as the base band signal. It is centered around the zero frequency. Now, to transmit those signals, what we are going to do is we are going to take the in-phase component, S1t, and we are going to multiply it by cosine 2 by fct. And this fc is the carrier frequency. Here we are doing the modulation. And we are going to take the quadrature part, and we're going to multiply it by sine 2 by fct. So if you do this analysis in the time domain, this is equivalent of having a complex envelope. So we're going to have like an envelope, like a mirror of the signal around the t-axis. So it's going to be something like this. Okay, and then the cosine is going to be here inside this envelope. It is like really similar to the AM modulation. Okay, and we are going to do the same here for the complex part, but we are going to multiply that by a sine. So the signal we are having here is going to be something like this. So if you want to look at things in the frequency domain, multiplying a signal by cosine, it's like having two replicas of the signal around fc and minus fc. So we're going to have two sync. Same for the imaginary part. We're going to have two replicas of the quadrature signal. Okay, so now we want to transmit both of those signals, both the in-phase part and the quadrature part. One way to do that is to transmit the signal first, and the receiver has to wait for this transmission to end. Then we transmit the signal. So the receiver has to wait for the in-phase part, then the quadrature part, in order to reconstruct the signal, which is not so efficient. Another alternative is to transmit them at the same time. And how to do that? We're gonna make an interference between those two signals. So we're gonna create a new signal, which is basically the in-phase modulated part minus the quadrature modulated part. And we are gonna send this signal. Now, if you really think about it, the receiver doesn't care about this cosine part or this sine part. It cares only about this in phase part and the quadrature part. So the question is, if we transmit this signal, we're kind of making an interference between the in phase part and the quadrature part. So can the receiver separate those parts? And the answer is yes. Okay, let's see how that happens. So if the receiver wants to get this part of the signal, like the in phase part is IT, it's gonna multiply the received signal ST by cosine 2 by FCT. And let's see why this works. So we're gonna have RT, the received signal. ST, remember, is the in phase component of the signal multiplied by cosine 2 by FCT. Then we have minus the quadrature part multiplied by sine 2 by FCT. And we are going to multiply all of this by cosine 2 by FCT. Now, let's distribute this cosine here and there. So this should be SIT cosine squared 2 by FCT minus SQT sine 2 by FCT cosine 2 by FCT. Now we're going to use some trigonometric inequalities. The first one of them is cosine squared x equals half plus half cosine 2x, to expand this one over here. So this one is going to be SIT multiplied by half plus half cosine 4 by FCT. Okay, then we are going to use another trigonometric inequality, which is basically sine half sine 2x equals sine x cosine x, to expand this term. So what we are going to have here is minus half SQT sine 4 by FCT. And let's expand this. So this one is going to be half SIT plus half SIT cosine 4 by FCT minus half SQT sine 4 by FCT. Now, here where the magic is gonna come. So we have three signals added to each other. Let me like denote them as, this is the first signal, and this is the second signal, and this is the third signal. They are still convoluted in the time domain, but if we look at things in the frequency domain, we are gonna see that we have this first signal is gonna be centered around the zero frequency. Okay, so this is the first signal in the frequency domain. The second signal is gonna be the in phase component multiplied by cosine, and this is gonna be just two replicas of the in phase signal. So this is the second signal. The third signal, this one, is going to be half multiplied by SQT multiplied by sine. So it's going to be like two other replicas around the same carrier frequency, basically. So if you look at it, if we apply low pass filter, we can obtain this signal over here, which is basically the first part of this summation. And if we multiply that by 2, we are going to get the in-phase part of the signal, which is this guy over here. So this is good. We were able to obtain the in-phase component of the signal. And if we multiply this received signal by sine instead of cosine and apply similar analysis, we will be able to obtain the quadrature part of the signal. So this works. We're able to transmit the real and the imaginary part of this modulated signal. So just to repeat those definitions, because they are really important, and we are going to use those terminologies a lot in the future. The baseband signal or the complex envelope signal is basically the in-phase part plus j multiplied by the quadrature part of the signal. And this is the baseband signal because it is centered on the 0 frequency. If we move that to higher frequencies by multiplying by cosine and sine, we're going to construct what's called the bandpass signal. And this bandpass signal has another representation, which is the real of ut multiplied by the complex exponential j2 pi fct. If you expand this, you're going to see like it's the same as this expression over here. Okay, so this is a transmit signal. We are going to transmit this over air. At the other end, the receiver is going to receive a distorted version of that signal. So the receiver is going to receive a reel of VT signal, and this VT is a function of the transmit signal and the channel response. And if we are talking about linear time invariant system, this is simply a convolution between UT and HT. And this is the bandpass. I mean, this is these cosine and sine terms over there. And then we are gonna have an additive noise, which is caused by interference from other electromagnetic signals, for example, along the way. So this is the signal the receiver is gonna receive at the other end. So the main messages that I want to convey from this video is this expression over here for the received signal and this expression over here for the transmit bandpass signal. We are going to use those expressions a lot in future videos. So thank you very much for watching.